Okay, in this segment we're going to be taking a look at one more application of that 4-transistor translinear loop that we've been looking at. And this circuit looks like the following. So these two collectors are tied up to VCC. Our input current is IX over here. Two other input currents which are constant. We're going to call them I tau. And we've got a funny looking element over here, which is a capacitor, C, and our output current is I sub Y. We'll call the voltage here in the capacitor V. And here we're going to make our standard assumptions about the transistors being ideal. No base currents, no early effects, so we're going to assume same matching and same temp. We're going to be assuming beta goes to infinity and VA goes to infinity. And we're going to be assuming that V out, standard thing, V out high enough to ensure output transistor is in forward active mode or soft sat. So there's some place for IY to flow from. Here IX is time function of now a function of time. These are constant. Okay, and our goal is going to be to find an equation that describes the behavior of the system from input to output. Okay, the first thing to do is to think about, well, are these 3 transistors which we're not guaranteeing are forward active by hypothesis, are they going to operate in the forward active mode? Well, this transistor and this transistor, these 2 transistors are both like emitter followers, as we've been talking about, and the input voltage here, the base voltage of them, is basically 1-2 VBEs above ground, roughly in the range of maybe 0.8 to 1.4. And VCC is our most positive power supply here, and so that could be 5 volts, it could be 3.3 volts, but it's certainly more than the typical 1.4 or so that we would expect to be the maximum value for the input voltage here. So these 2 transistors are guaranteed to be in the forward active mode. They're going to be carrying I tau, so their base emitter junction must be forward biased. In other words, the emitter must be lower than the base in order for that current to come from somewhere. And moreover, the base emitter voltage of this transistor is the amount by which the collector is higher than the base of this transistor down here. And so this transistor is biased further into the active mode than the diode-connected transistor would be, where the base and the collector are at the same potential, because this is about a diode drop or a VBE higher than this point. Okay? So all three of these transistors are going to be in the active mode. We're assuming that this one is in the active mode. And the question is, do we see this translinear loop in this picture? Well, there's a twist in it, but we go up here, down, and back down to ground. So the answer is yes. So we go up one base emitter rise, up a second base emitter rise, and then we go down one base emitter drop, and then we go down one base emitter drop back to ground where we started. And so our circuit does have that that translinear loop in it. And so what are the collector currents? Well, the collector currents are going to be Ix, our input current down here. This one's going to be I tau. This one, what is this one going to be? Well, you might be tempted to say it's going to be I tau. And if Ix is not moving and the circuit is at a steady state, that would be true. But if we have some capacitor current here, IC, then by KCL, we're going to have this current is equal to I tau plus IC. So we're going to call this current, let's say I sub P. Okay, so KCL at node V tells us that I sub P is equal to I tau plus IC. We know that the translinear principle around our loop tells us the product of Ix times I tau is equal to IP times IY. Okay. We also know that the cap implies something about the relationship between V and IC. So IC equals C times dV dt. We also know something about the relationship between V and IY. So the forward active model tells us that IY is equal to IS e to the V over UT. Okay, so let's call this equation 1, equation 2, equation 3, equation 4. Let's do, since we need to know something about dV dt, and we'd really like to eliminate V from our description of the system, we can relate diy dt to dV dt through differentiating the forward active model here in equation 4 with respect to time. So d by dt of equation 4 implies that diy dt is equal to, well, differentiate the exponential. We get is times the same thing, times by the chain rule, 1 over ut times dV v dt. And this, of course, is just Iy. We can back substitute in equation 4 in here. And so we have a relationship between dv dt and diy dt that says that dv dt is equal to, well, ut over Iy times diy dt. So to get a relationship between the capacitor current IC and the output current, the output current here, we can basically multiply both sides of this equation by C. And so, or substitute dv dt into 3. So let's call it that. So we'll say 5. So 5 into 4, or rather 5 into 3 gives us that IC equals C ut over Iy times diy dt. Okay, so we'll call this equation 6. And now we can substitute in equation 6 into equation 1, and equation 1 into equation 2. So 6 into 1, and that into 2 gives us, on the left-hand side, we have Ix, I tau. And on the right-hand side, we're going to get I tau plus IC, which is in turn CUT over Iy times diy dt, and then we multiply that by Iy. Okay, so this whole thing was IP. And this thing up here was IC. Okay, so that's the governing equation of our circuit. We're going to do some things with it. The first thing we're going to do is create some space. Okay, so we're going to move up here. We'll leave that down there for reference. So the first thing we're going to do is, on the right-hand side, we're going to multiply everything through by Iy. Actually, we're going to flip this around so that we exchange the left and right-hand sides of the equation. So, and then we're going to take what now is going to be the left-hand side of the equation and distribute the Iy through here. So we get Iy I tau plus CUT times diy dt equals Ix times I tau. And now we're going to divide both sides of this equation by I tau. And we're going to swap these two terms here. So swap these So that means we put an I tau downstairs over here, CUT over I tau times diy dt. We divide this term by I tau, we're just left with an IY. And on the right-hand side, we're left with an IX. So this is a kind of a curious situation. What kind of differential equation is this? Well, all of the terms here are just linear terms, and the derivatives of IY are just linear. There's only one, and it's the first derivative. So this is a linear ODE. It's first order. And the question is, what is this thing here? Well, this is a capacitance times a voltage. And if you recall from the capacitor discussion, for a linear capacitor, Q equals CV. And so the units of the numerator of that ratio is charge, or is units of charge, so it's coulombs. And the denominator is a current, which is coulombs per second. So this thing has units of time. So it's the capacitor that we put here in the circuit. Might have a value of some number of picofarads, let's say, if it's an on-chip capacitor. And then the UT is the thermal voltage, 25 millivolts at 300 Kelvin. And then I tau is this constant current that we're supplying. And so if I tau is constant, then this thing has units of time, and it's constant, and so this is a time constant, tau. And so substituting that in, we have here an equation which is tau times diy dt plus Iy equals Ix. So this is a first order linear ODE with constant coefficients. Now, that may not be something of a surprise to you or a shock to you, but it should actually shock your socks off, because this is a large signal analysis of a circuit built with really nonlinear devices. These devices with exponential IV relationships are about as nonlinear can be. And yet, end to end, the system is described by a linear differential equation. So this is an end-to-end linear system from the outside, externally linear, but internally, if we were to look at, let's say, the voltage on this capacitor, if we put a pure sine wave in, we would notice it's distorted. It's got some sort of funky compression going on. But in this particular type of circuit, we use the nonlinearities of the transistor and the fact that they match each other and are very predictable in a coordinated fashion so that we can achieve end-to-end linear behavior. In fact, this is the same ODE that would govern, so if I were to make an RC low-pass filter, let me just call this Vx and Vy RC. if I were to do the KCL and write down the ODE I would get RC times dvy dt plus vy equals vx, and this would be tau, the time constant. So these two systems are governed by the same equation. So this is a first-order low-pass filter. So then this is also a low-pass filter, first-order low-pass filter. This is called a log domain filter. This is not a fluke. These circuits can be systematically designed to be filters of arbitrary order. We can basically start out with a transfer function and systematically come up with effectively a translinear circuit with capacitors in strategic locations that basically embody that transfer function. So the question arises, well, this seems hard, and this seems pretty easy. I can just go grab a capacitor, I can grab a resistor from the stockroom, I can hook them up, and I got my filter. And these are voltages, and what's with this thing? Okay, well, a couple of things to think about in that connection. First of all, when you're dealing with designing integrated circuits, the economics of components are completely different than they are when you're building discrete circuits. So capacitors are pretty large devices, but they integrate pretty well, because integrated circuits, as we'll learn in a while, are basically fabricated by having a thin layer of conductor separated by a thin layer of insulator separated by a thin layer of conductor, and that's a formula for making a pretty good capacitor. You basically put down a layer of conductive material, you pattern it using a photolithographic process, then you put down an insulator, you put down another layer of conductor, you pattern that second layer of conductor, you then put down a third layer of conductor, a second layer of insulator, third layer of conductor, pattern the third layer of conductor, and so it's all these little sandwiches of conductive material separated by insulators, and that's a capacitor. So capacitors are very easy to integrate. They can get quite large. A typical on-chip capacitor, a very large on-chip capacitor, might be 100 picofarads. You can't really make a capacitor that's much bigger than that on a chip, realistically. So we typically will use capacitors that are kind of in the range of maybe a few hundred femtofarads to a few picofarads, or maybe 10 picofarads, something like that. That would be a typical on-chip capacitor size. Transistors are extremely cheap. You can put probably hundreds of transistors in the space that it would take to make, let's say, a 10 picofarad capacitor, if not thousands. Resistors are really big, unless you've got a very, very specialized process option which allows you to make reasonably small resistors. But most of the layers that you have available in an IC process are pretty conductive, and so to get a high resistance, you need to basically make a very, very thin wire of material snake back and forth, back and forth, back and forth. And to get anything other than maybe a few hundred ohms or so takes an enormous amount of area. And so while this may seem like it's a very easy thing to do with discrete components, it turns out something like this is much easier to do on an integrated circuit. So that's one thing to note. It's just that you can send 1,000 transistors to do the work of a single resistor. if you want to without any difficulty. The other thing to note is that once I pick an R and I pick a C, the time constant of this filter is fixed. Whereas over here, what sets the time constant of this filter? Well, this is set by the capacitance times the thermal voltage divided by this current I tau. That means that I have an electronic control through these current sources here of the actual time constant. So the same exact circuit with a fixed size capacitor can be tuned electronically after fabrication. So I can basically set this current level to get whatever time constant I want, given the size of the capacitor. What kind of range do I have available to me to tune these currents over, assuming, let's say, that they're made with NPN bipolar transistors? You've seen that now in Lab 3, that I can basically get currents that go from nanoamps up to milliamps, right? That's a 6th order of magnitude tuning range. If I bias these currents down here for, let's say, a picofarad capacitor, if I bias these currents down here at a nanoamp, I'll have something that has cutoff frequencies maybe in the audio range, in the kilohertz range or something like that, or hundreds of hertz. But if I tune this up to the milliamp level or so, I can very easily get into the RF front end kind of hundreds of megahertz to gigahertz corner frequencies. So not only do I have an ability to change the time constant or the corner frequency of my filter through this electronic control, I have the ability to do so over a very, very wide dynamic range. And so that is super, super cool. So again, the actual synthesis of these circuits is something that is going to be well beyond the scope of what we're going to be able to cover in this class, but I wanted to kind of give you a sense that this is out there, and it's the same translinear loop that we've been looking at that can do the static nonlinear functions, can also do this dynamic constraint. And you can actually mix and match the translinear circuits with the static nonlinearities with these sort of filter functions to make nonlinear dynamical systems with very precisely prescribed dynamics. Anyway, this is a really cool thing that is very surprising, and I think it's cool. I don't know, your mileage may vary, but I think it's really cool. So anyway, that's it for this segment. See you next time. We'll talk about base currents and their effects in translinear circuits and how to mitigate them.